Bismillah ar-Rahman ar-Rahim. Welcome again. This is the third video about the calculation of the apparent power in the three-phase systems. How to calculate the apparent power in terms of phase quantities or in terms of the sequence. I'm going to introduce an example to show how the calculations on the three-phase system takes place, in particular the three-phase power. We can calculate the three-phase power as we shall see. This is the example. As you see, we have a balanced positive sequence Y connected source. We have a source 180 volt with 0 degrees. This voltage is applied to a balanced delta connected load. We have a load, not this load, a load. The connection of the load is delta. The value of the load is 30 ohm with a degree of 40 degrees. The source and the load are connected by a line with an impedance of 1 ohm and an angle of 85 degrees. The requirements of the problem or example: the first one to find the line currents, and the second requirement to find the delta load currents, and the third requirement to find the voltages at the terminal of the load. So we have a delta load, delta connected load like this, and this is the third phase of the connected load. Each one of these is equal to 30, and the angle between the voltage of the load and the current passes through the load is 40 degrees. 40 degrees. This is also 30 is a symmetrical load. Okay, and we have a source to supply voltage to this load. For the reason to simplify the system, we have to convert the delta connected load to a star connected load. So we have to a star equivalent load, equivalent connected load. This is the star connected load. The star connected load, as you know, is equal to 30 divided by 3 and an angle of 40 degrees. This is equal to 1040 degrees. And also this one is equal to 2040 degrees. Okay, so we have here two loads, the delta connected load and the star connected load, and the two loads are equivalent. We have here a source. Okay, here we have phase A, we have here phase B, and we have here phase C. Okay, IA, IB, current in phase B, and here we have the current in phase C. Okay, and these are connected to the source through an impedance of a line. This is the line. This is the line. A, this is C, and this is B from the source. Okay. Now, to find the line current, we can take a single phase of this system. Since the system is symmetrical, the source is symmetrical, the transmission line is symmetrical, and the load is symmetrical, we can take a single phase of the system. Here, this is the single phase of the system, EA, okay, connected to the phase A of the line, and this is the phase A of the load. phase A of the star-connected load. By means of the star connection of the load, we can take the single phase diagram of the load. This is equal to, as seen by the example, 1 ohm and this is equal to 10 with an angle of 40 degrees. And now we should calculate IEA. Since the voltage between A and B in the source is equal to 480 volt and an angle of this is AB. This is the voltage between A and B in this source. As you know, EA is equal to EAB, magnitude of EAB, divided by the root of 3, and the direction of EA lags the direction of EAB by 30 degrees. So the angle of EA is 0 minus 30 degrees volt. So EA is equal to 480 degrees divided by root 3 and a angle of 30 degrees. Here is the vector EA, and this angle is 30 degrees EA. Okay, so the voltage EA is equal to this value, this quantity. Now, if we want to calculate IA, it is simple to calculate IA. IA is equal to, as you see from the single line diagram, that the voltage EA is applied to the impedance of the line and the impedance of the load. So IA is equal to 480 divided by root 3. This is the voltage EA applied on the impedance of the line plus the impedance of the load. Equal to the value of 25 0.83 and an angle of minus 73.78 degrees ampere. So this is the vector IA. This is the vector IA. And this is the angle minus 73.78. Okay. Now we can find the current IB. For instance, we need the current IB since the voltages are symmetrical and the load is symmetrical, so also IB is equal to 25.83, the same magnitude, and logs the current IA by 120 degrees minus 73.78 minus 100 degrees, and this is equal to 25.8 minus 193.78 ampere, and so on. I see same manner is equal to 25.83, and the angle is IC is leading IA by 20 degrees because the currents, as you see, this is IB, this sorry, we have to IB 100 degrees, so this is IB, and this angle is 120 degrees, and IC is here, and the angle is 120 degrees. So IC is equal to 25.83 with an angle of 46.22 ampere. This is the first demand, how to find line currents. This is the line currents. The current in phase A, the current in phase B, the current in phase C. Okay, these currents we have already calculated these currents. Now, if we want to calculate the current on the delta connected load, we want to find IAB, for instance. Okay, IAB, and we want to find IBC, and this is ICA. How to find IAB? Is the current IBC. How to find IAB? Okay, this current is less than the star connected load current by the root of 3 and leading the current of the star connected load by an angle of 30 degrees. So the current IAB current IAB equal the current IA is equal to 25.83. Okay, the angle is minus 73.78 plus 30 degrees. The current IAB leads current IA. This is current IA. Leads current IA by 30 degrees divided by the root of 3. This is equal to 14.91, and the angle is minus 43.78 degrees ampere. Okay, and the same manner we can find IBC. Okay, IBC equals to also 14.991, and the degree of minus 163.78 ampere, and the current ICA equals to 14.91 with the degree of, because the current ICA leads IAB by 120 degrees. So the angle of the current IC is equal to 76 point ampere. These are the currents of the delta connected load. Second requirement of the example. Now, if we want to find the voltages of the load, the voltage VAB, the voltage between A and B, this voltage, VAB, okay, between the terminal A and B, and the voltage between B and C. Okay, and the voltage between point C and A. As you see from the diagram that VAB, the AB is equal to the current flows through the delta connected load, the current IAB. This is the current IAB multiplied by the impedance of the delta connected load. The current, as we see on the delta connected load, is equal to 14.9, and the angle is minus 43.78 multiplied by the load of the delta connected load, 13, and the angle 14. This voltage is equal to 447.3, and the angle, as you see, minus 3.78 degrees volt. This is the voltage between A and B. This is the voltage between A and B. The voltage between B and C, these are symmetrical voltage. So the magnitude is the same, 447.3, and there is a displacement between them equals to 120 degrees. So the angle of the voltage VPC is equal to minus 123.78 degrees volt, and the voltage VCA is equal to 473, and the voltage VCA leads VAB by 20 degrees. Okay, so the angle is equal to 100, 100 16 point 20 degrees volt. Okay, these are the voltages at the terminals of the load, at the terms of the delta connected load, the voltages that we have plotted in the figure. These voltages, they are asymmetrical voltages. Now, suppose that, assume that we need to calculate SP of the load for the delta connected load. The power of the delta connected load, the apparent power, which is equal to P plus JQ. This is the active power of the load, and this is the reactive power of the three-phase delta connected load. Okay, how to find SP, the apparent power? As we told you in the previous lectures, since the load is symmetrical, then the power in each phase are equal. Okay, the power in each phase of the delta connected load are equal. The power consumed by this phase is the same as the power consumed by the second phase, and the same that consumed by the third phase. The formula that we can calculate the apparent power is as follows. Been written in the second or the power SP for a three-phase symmetrical load is as follows: 3 multiplied by the voltage of the phase, the voltage of the phase is equal to VAB multiplied by IAB conjugate. This is the formula for calculating the apparent power. This is the phase quantity of the voltage, and this is the phase voltage of the current. The voltage of VAB, this is the voltage of VAB. This is the voltage of VAB. Okay, this is the voltage of VAB. And the current IAB, this is the current IAB. Okay, these are phase quantities. So SP equals to 3 VAB, as we said, 4 multiplied 407.3 angle 3.78. Plus rewrite it again. Okay. P SP is equal to 3 multiplied by 147.3 minus 3.78 multiplied by the conjugate of the current IAB. This is the current IAB, sorry, with the magnitude of 14.91, and the conjugate of this vector is the picture of this vector, as we said in the past video. So the angle here is 43.78. Okay, and then SP is equal to 20,000 and 7.7 with an angle of 40 degrees. Volt ampere. Okay, this is the three-phase apparent power on the delta connected load. This power is equals to P plus JQ. Okay, then P is equal to 20 thousand 20,000 and 7 cosine the angle 14 plus J 20,000 point 8 sine the angle 40 degrees. Okay, this is the active power. This is the active power P, and this is the reactive power Q of the delta connected load. Okay, now suppose that we need to calculate S of the load. We need to calculate the three-phase power of the load by means of sequence components. Okay, now we want to calculate SP by means of the sequence component. Okay, we have the system is symmetrical. That means the zero sequence current, zero sequence network, and the positive sequence network and the negative sequence networks are uncoupled. They are uncoupled. Okay, the three sequences are uncoupled, which means that I naught is equals to 0 and I2 is equals to 0 because the three sequence networks are uncoupled. Since I naught is equal to 0, it means that V naught is equals to 0 and V2 is equals to 0. Okay, the zero sequence quantities are 0 and the negative sequence quantities are also 0. Okay, this is for the symmetrical system only. The symmetric because the system is symmetrical system. Okay, and the load is symmetrical system. Thus, IAB, okay, IAB is equals to IAB naught plus IAB1 plus IAB2. Okay, and this quantity is 0 and this quantity is 0. So IAB is equal to IAB1 in this case. Okay, the same as for the voltages. We can write the same for the voltages. Okay. Also, we have VAB is equals to VAB naught plus VAB1 plus VAB2. Okay, we said that V naught, the zero sequence currents are zeros and the negative sequence currents are 0. It means that VAB is equals to VAB1. Okay. Now, the formula of the equation that enables us to calculate the apparent power using the sequence components is written as follows. 3 multiplied by V naught plus V1 plus V2 multiplied by I naught conjugate I1 conjugate, I2 conjugate. This is the general formula. This is the general formula for calculating the three-phase formula. This formula. This is the formula. This is the formula for calculating the three-phase current. Okay. Now, this delta connected load V naught is 0. So SP 0. So 3 multiply 0. This quantity is 0. V1 is VAB. VAB. And we know that VAB here is the VAB. This is the VAB. Here is VAB. This is okay. So VAB is equal to 470, 47, 447.3 with an angle of minus 3.78. Okay, and V2, as we said, is equal to 0 multiplied by the column vector. I naught, we said that it equals 0. I1, IAB1 is equals to IAB, and this is IAB conjugate. It equals to 14.91, and the angle is 43.78. And I2 is equals to 0. Okay? If we multiply the two matrices, the row matrix by the column matrix, and multiply them by 3, then SP is equal to the same quantity, 20,007.7, and the angle is 40 degrees, volt ampere. Okay, this is as you see. This is the how to calculate SP using phase quantities. And this is how we use the sequence quantities. Sequence, what I want to explain to you. When we use the phase quantities, and in the unsymmetrical cases, we use the sequence quantity.